this integral over the fundamental domain of f of tau, g bar of tau, v to the k, du dv divided by v squared. And then if we want to regularize this, we'll just truncate our fundamental domain at a height t, and we take the limit as t goes to infinity. Okay. So this is our regularized inner product, and this regularized version of the inner product, this works for anything weakly holomorphic, weight k, for the first argument, and then we'll use our second argument to be a Cuss form. Our complex numbers. Okay. Now, Bruinier and Funke use this regularized inner product to define a very important pairing operator that involves harmonic Maass forms. Okay. So this is the Bruinier-Funke pairing. And this is, we'll just use curly brackets here, but this is going to go from weakly holomorphic modular form of weight k cross a harmonic Maass form of weight 2 minus k. And again, the result will be a complex number again. But this is just defined to be, so the pairing of f and, let's say, I'll use capital G to be our harmonic Maass form here. This pairing is simply defined to be the inner product of f with the Xi operator acting on G. Okay? Now recall, Xi acting on G is going to be a Cuss form, so this fits nicely with our definition over here. Okay? Does that make sense? Yeah. Oh, yes. Thank you. Good. Okay. Any questions on this so far? So far, this looks like a fairly simple definition. It's maybe not very obvious why this is useful for us, but it turns out that this pairing is extremely useful based on the following result that was proven by Bruinier and Funke. And this is going to rely on the Fourier expansions of f and g. Okay. So we're going to write f of tau, we're going to write a Fourier expansion for this using coefficients a of n, q to the n. Okay. So again, this is weakly holomorphic. And so we're going to say n needs to be bigger than minus infinity. So this just means at most finitely many negative terms there, right? Now our Fourier expansion for g, well, we're going to rely specifically on the holomorphic part of this. I'm not going to worry about the non-holomorphic part, but let's say that our holomorphic part of this is going to have a Fourier expansion, again, similarly, index over at most finitely many non-positive terms. And then I'll just write this b plus of n, q to the n. Okay. In this case, Bruinier and Funke have this formula for the pairing. The pairing of f and g is equal to the sum of a of n, b plus of minus n. Okay. Now I can just write this as a sum of n over the integers, but there's only finitely many terms here, right? So n is allowed to be negative, but there's only finitely many negative terms here. N is allowed to be positive, but there's only going to be finitely many non-zero terms over here. Okay, is that clear? Okay. And then we're just really quickly going to note this is the constant term of f times g. Okay. So that's where this sum comes from. Okay. Now the proof of this, I'm not going to go through the full proof, but it's a pretty simple application of Green's theorem. Okay? And so basically, what is Green's theorem going to do for us? Our initial, well, we use our definition to look at our inner product here. That's an integral over the interior of this truncated fundamental domain. Green's theorem is going to allow us to step back for an antiderivative of this function, okay? But then we're looking at a contour integral around the boundary, okay? And the integral around the boundary, okay? Of course, we're integrating in the usual counterclockwise way. Everything down this edge is going to cancel with the integral up this edge, right? Our modular forms have the same value on those. Okay, and then the same thing across here. This half arc matches with this half arc. Okay? And so everything there vanishes. The only thing that plays into any role in this actual calculation is going to be the integral across the top of our truncated fundamental domain. And what that is going to do for us is it is going to just capture this constant term. Okay, so those are the details there. If it's not clear how to finish everything, I'd recommend taking this as an exercise. Again, it's just a simple exercise in Green's theorem, but just work out the details on that. Okay. Is that clear? Any questions there? Okay. So this is a very important theorem for the theory of harmonic Maass forms, and it gives us a lot of very important applications almost immediately from this. So let's talk really quickly about some of those applications. Okay. The first application is that every harmonic Maass form, so let's just say every G in H of 2 minus K has a principal part. Okay, has a non-trivial principal part. Okay, can anybody see how I could get that immediately from this pairing? Here's maybe the first step that we would look at. Let's just take the pairing of C of G against itself, against G. Okay, what is this? Well, this is just going to give us the inner product. I'm just going to write this as, I'll use the Peterson norm, okay, of C of G, okay, which is going to be non-zero unless C of G is 0. Okay. So let's see, I should actually add a hypothesis here. Every well, let's see, every G not equal to 0 in H2 minus K, right? Okay, so this right here is only going to be 0 if G is weakly holomorphic. Okay, because we know that the Peterson inner product is positive definite. Okay, so equals 0 only if G is weakly holomorphic. Okay, we already know that weakly holomorphic modular forms for negative weight have to have a pole. Okay, and so in the case that this is non-zero, well, then we can look at this calculation. The only way that this has non-zero terms is if I have a principal part. Okay. Otherwise, formula implies G has principal part. Okay. Is that clear? I know I'm kind of sketching that. I can go into more detail if we need to. Yes? The principal part? Yeah, so that is for G here, yeah. So that's going to be the terms here with n negative. right? So in this formula here, I need to have terms with n negative because C of G is just a cusp form. So these A of n terms are only going to show up with n positive. So in order for anything in this sum to make sense, I need to have some terms with n negative, to be non-zero, rather. Is that clear? Okay. Now, so every harmonic Maass form in H2 minus k has a principal part. I can make this a little bit stronger. That means it's uniquely determined by the principal part. Okay? And that just follows because if I have two harmonic Maass forms with the same principal part, their difference would have to be 0. So forms in H2 minus k are uniquely determined by a principal. Okay. Now, let me take a small deviation before we get to the next application of the pairing. But it just kind of builds on this point here. And this is simply that I can choose basically whatever principal part I want, at least up to the constant, and there is a harmonic Maass form with that principal part. Let me make this part 3. Well, I'm not going to call that part 3. Let me just call this a claim. This doesn't follow from the pairing. This is kind of its own piece here that I need for the next step. So for each positive integer, so let's just say n in the natural numbers, there is a unique form, say h sub, so I'll have the 2 minus k and n. Let me write this bigger down here, h of 2 minus k comma n, which is going to equal q to the minus n plus big O of 1. Now I should add another hypothesis here. I need k to be bigger than 2 for this to make sense, or for this to be true the way that I've written this. In the case k is equal to 2, I'm looking at harmonic Maass forms of weight 0. In that case, it's not unique because I have constants that I can adjust. And so in that case, k is equal to 2. Then I have h of 2 minus k comma n is equal to q to the minus n plus big O of q. Okay, so I can pick basically whatever I want for the principal part except possibly the constant. Okay, and I have a harmonic Maass form with that shape. Now, this is something, there's a few different ways to prove this. The simplest way that I know just uses the Poincare series, the Maass-Poincare series. And Ranveer did a great job of discussing these yesterday. Okay, Nick will also talk a little bit more about those in his lecture later today. I'm not going to talk about those. We'll pass on that for the moment. But that is one proof of this fact. Bruinier and Funke also give a geometric proof of this fact. Okay. But that's good enough for our purposes. I just want to make this claim out here. There is such a harmonic Maass form that exists for negative weight. Okay, I can pick this principal part. Okay. Well, the J function works perfectly fine in weight 0. For negative weight lower than that, that's only going to get us, we can only use that to get weakly holomorphic forms, right? And that doesn't work the moment that there are cusp forms. Yeah, weight 0, perfectly fine. weight 0, level 1, that's perfectly fine. But yeah, the moment there are Cuss forms, we need true harmonic Maass forms. Okay, so now using this fact, this allows us to get to a couple of other results very quickly. Where's that, 2? Say 3. Nick stated this fact just a moment or yesterday, but I can use these functions right here very quickly and the pairing to show that the Xi operator, which takes us from h of 2 minus k to sk, this is surjective. Okay. So this is a very useful fact. It's easy to kind of gloss over, forget about that we kind of rely on this a little bit. I think, Nick, you used a proof of this. Did you talk about this?
I did talk about it. I didn't prove it.
Oh, okay. But you were going to prove this using Poincare series, right? Okay. So there is a nice proof of this using Poincare series. Nick will come back to this. I want to talk about this in terms of the pairing. Okay. Again, if I take f to be a Cuss form in Sk, and let's say that f of tau is equal to the sum of coefficients an q to the n. It's a Cuss form, so this is going to be n equals 1 to infinity. It turns out then that the pairing of f with this harmonic Maass form, h of 2 minus k comma n, okay, the formula for the pairing is going to pick out just the nth coefficient of f of tau. So this is going to be an. Okay? And so in particular, I can write this formula for f of tau to be the sum from n equals 1 to infinity of the pairing of f against this harmonic Maass form. Okay. Now the point here is if we assume that the pairing, if we assume that the Xi operator is not surjective, then I should be able to pick some Cuss form that's orthogonal to the image. If f is in Sk and f is orthogonal to the image, Xi of h of 2 minus k, well, then using this formula down here, say formula 1, let's go ahead and call this 1 right here. Then using formula 1, you end up getting that f is just identically the 0 function, right? They're orthogonal to the Cuss forms, or the image of Xi of h. And so we go through each of these coefficients. Each one of those coefficients has to be identically 0. So the function itself is identically 0. Okay. Does that make sense? Okay. If it's orthogonal, the space Xi 2 minus k acting on h 2 minus k. And so I look at the image of the operator acting on the space. So if this is not the full space, then I should be able to find something orthogonal to that space, which then tells me this formula would have to be 0. Good. Is that clear? Okay. Again, this is one of these facts. There's several proofs of it. I like this one because it relies on the inner product. But again, we'll see it later with the Poincare series, and I'm sure there are several other proofs of this fact. I believe Zwegers has a rather direct proof, but it involves a potentially meromorphic, holomorphic part of the harmonic Maass form. I don't know the details of that proof though. Okay, let's see. What's the next one that I wanted? Oh, yes. The next one here I'll call this application 4. This is Borchard's obstruction theorem. Now, if I write this as an application of the pairing, this is a very different proof than Borchard's proof. Borchard's proved this using Serre duality, but basically what this theorem is going to tell us is how can we figure out what principal parts actually rely or actually belong to weakly holomorphic modular forms as opposed to harmonic Maass forms. Okay? And so what Borchard's theorem says is, so let's let p of x be a polynomial. Then p of q inverse, so I'm taking my polynomial, evaluated at q inverse. This is a principal part. This is the principal part of some form in M2 minus K bang. Okay, so it's a principal part of something weakly holomorphic if and only if product P of Q inverse times G of tau has no constant term for all G of tau in, let's see, we need holomorphic modular forms of weight K. Okay. So if we take some basis for these holomorphic modular forms, okay, we look at this product here against our proposed principal part, that constant term needs to be 0 for every element in that basis. If it passes that test, then there is a weakly holomorphic modular form with that principal part. Okay? Does that make sense? Okay. Now, the way that we can prove this, again, Borchard's proved this using Serre duality. Okay? We can get this using the pairing, but basically this kind of tells us that the pairing is somehow sort of an analytic interpretation of Serre duality. But the way that we would prove this using the pairing is basically I can construct a harmonic Maass form with this principal part, and then I'm looking at the inner product with G of tau. That at least works for the Cuss forms. It doesn't quite work with the Eisenstein series, but it's the same idea. Okay. So we would construct some kind of f of p, which is equal to P of q inverse plus big O of 1. Okay. I can't necessarily pick my constant for my harmonic Maass form. Okay. Then from here, I do my inner product, or my pairing, G of tau against Fp for each Cuss form. Okay. And then if I look at the pairing with the Eisenstein series, that's going to tell me what the constant has to be. Okay. My principal part had better match with the constant term that I get out from my pairing with the Eisenstein series, but that's what I'm looking for. Okay. Does that make sense? Okay. Yes, so this is going to be some harmonic Maass form that has this principal part. Okay, using that basis theorem that we just talked about, I can construct one, at least up to the constant term here. And then I just look at the pairing with this thing. Right. Yes, so the constant term, remember the formula for the pairing gives me the constant term when I do this multiplication. Right? So Borchers wrote this just in terms of the constant term of the multiplication. Bruinier and Funke do this in terms of the contour integral, but you end up pulling out that constant. Yeah.
That the H2 minus Kn has a pole of order n.
Yeah.
Why not just take linear combinations of that according to your polynomial P?
Yeah. So that's what I would do to construct a harmonic Maass form with that principal part. And then the question is this weakly holomorphic or simply a harmonic Maass form? And that's where, if we do our pairing and we always get 0, it'll be weakly holomorphic. And that's the same thing as Borcher's theorem. Does that answer the question? Yeah. Good. Okay. So this is a good place to move into some of the examples that I wanted to talk about. So today's lecture is supposed to be on examples of harmonic Maass forms. Okay. And maybe the first place to talk about these examples involve our weakly holomorphic modular forms. Okay. So let's see, Ranveer yesterday talked about these functions, these JM functions. Okay, these actually form a basis for M0 bang. Okay, and they have this shape, Jm is equal to q to the minus m plus big O of q. Okay. Now we also have weight 2 forms. I'm going to call these, well, I'll call them IM in M2 bang, and these are going to have the shape, again, q to the minus m plus big O of q. Okay, in weight 2, we don't have any holomorphic forms. Okay, E2 doesn't count; it's not a holomorphic modular form. Okay, and so once again, these form basis, I guess up here I can say m is bigger than or equal to 0. Down here, m needs to be strictly bigger than 0. Okay. And we have this result. These were studied by Asai, Kaneko, and Zagie. Asai, Kaneko, Zagie also did this. Who's the other person that I'm? Asai, Kaneko, and Ninomiya. That's the one. So they did this before Zagie did, though I first became aware of this phenomenon through Zagie. I think a lot of people did, but it was first Asai, Kaneko, and Ninomiya that did this. They studied these forms. So we're going to give ourselves some, so let me make this a little bit more explicit. Let's say Jm is equal to q to the minus m plus the sum of n equals 1 to infinity. And we're going to say a of m comma n q to the n. So we'll name all of these coefficients here. And then we have these ims, which are going to look again like q to the minus m plus the sum n is going to equal 1 to infinity. And we'll call these b mn q to the n. Okay. And we have this really beautiful duality result. And this is simply that a of mn is equal to minus b of nm. Okay. There are several ways to prove this, but one very nice way involves the pairing. And this is just looking at the pairing. We'll move over here. Calculating the pairing of, let's see, in against jm. When we do our formula for this, this is going to pull out for us a of m comma n plus b of n comma n. Okay? That's what comes out of this. But because these are all weakly holomorphic modular forms, this has to equal 0. Okay? Does that make sense? Now, Kaneko does a little bit simpler version of this that doesn't rely on the pairing itself. He simply notes that the product of these two is a weight 2 modular form, and everything in weight 2 has a vanishing constant term. They're all derivatives. Okay. Yes, we're in level 1. In higher level, you can do something similar, but you've got to look at contributions at all of the cusps. Okay. And that's generally true. The pairing works in any higher level. You just have to add up contributions from every cusp. Yes. Yeah. So this proof, this generalizes even when we've got harmonic Maass forms going on. Yes. So we always have this kind of duality showing up for these bases of harmonic Maass forms. And that's something that when we talk about Maass-Planck-Gray series, we'll see formulas for the exact coefficients. It's very easy to see that, but that proof doesn't give much motivation for why it's true. This shows why it's true. Okay, we can see immediately that these harmonic Maass forms always have this kind of duality. Okay. Does that make sense? Good. Let me look at, let's see. Oh, what, okay. Yes, but again, M2 shriek, everything there is derivatives in polynomials of the J function. Yeah, and that's again true for every genus zero group. You have the same sort of structure happening. Higher genus, that's where we care about harmonic Maass forms, kind of giving this sort of generating series. Yeah. Okay. Let's see. I'm going to really quickly show you another example. This is also level 1. I'm just going to write down a few coefficients of these. But what I'm looking at here is a canonical basis for the weakly holomorphic modular forms. Okay, Duke and Jenkins defined kind of a canonical way of describing a basis for our weakly holomorphic modular forms, where you're sort of looking at the order of vanishing or the order of the pole at infinity, but then you row reduce, make things sort of vanish as much as possible, basically make things look diagonalized. But if we look in weight 24, so k is equal to 24, and of course we've got our dual weight, 2 minus k is equal to minus 22. Okay, so I picked 24 because this is a weight where we have 2 cuss forms. Okay, we have an F24, F24 comma 2. This is using Duke and Jenkins notation for this basis. This is going to be a form that starts q squared minus 48 q and so on from here. This is actually just delta squared. Okay, we'll have an F24 1, which is going to be a q to the 1, 0 q squared, and then let's see, those are minuses for their notation, and then this is a 195. That's, let's see. What's that? Oh, sorry, that's a 3 there. Yeah, I'm looking at my notes. I think I got something off because my coefficients here say this next coefficient is a 195,660 q cubed. I think this coefficient is wrong. It matches on both sides, so I'm just going to keep writing this for a second. But this looks much too large to me. This is supposed to be a coefficient of a cuss form. So something here is wrong. If we look down in the negative weight, f minus 22, okay, we have a function that starts, the smallest order of a pole that we get is 3. This is going to start with a q to minus 3, okay? And then from here we get a plus 48 q, okay? And so what we're seeing here, this 48 is supposed to match with that 48. Again, with a change of sign as we change from one side to another, okay? Again, they have to, just looking at a pairing between these two. Okay. If I go a little bit further, f minus 22, 4. Okay, I get a form that starts, oh, there we go. So q to the minus 4. Oh, what am I doing? That's a minus 2 there. Q to the minus 4, and then I get to a minus 1080 q to minus 2. That's what I've got wrong. That's a 1080. Okay, and so once again, this 1080 matches with this minus 1080. Minus 2, dot, 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 dot. Yeah. And if you're interested in seeing this duality play out a little bit more, I'm happy to show you these coefficients. I just don't like writing so much on the board. But you can see this as far as you want to go. We can calculate plenty of these coefficients. You can see these large grids that all form up, that are all dual to each other. And these form what Zwegers called modular grids. Okay. But then, just right here again, these principal parts, you can see every one of these coefficients have to match with our holomorphic forms. You take the product between them, you get 0. That's what's going to tell you what each of these terms here in this principal part are supposed to look like. Okay. Let me move on. There's a little bit too time consuming to write out a whole lot more of these coefficients. And we've still got plenty more that I want to look at here. Sure. Yes. So, yeah, so this is what I would say. So Ranbir kind of talked about this yesterday. In weight 2 and 0, you end up getting a generating function, right? We end up looking at like, well, in my notation here, you look at like I1 and divide this by, so I1 of tau divided by J1 of tau minus J1 of Z, okay? I1 here is, well, it's really the derivative of the J function. So what we have here is a logarithmic derivative of this factor down here. And this is a generating function. It generates the entire modular grid that we've talked about. Rows and columns give you the I's or J functions, right? If you want to go to a higher weight, let's say we go to weight 4, okay? What you would do in this case, so this is weight 2 and 0. So if we want to go down to weight, say 4, and then its dual weight is weight minus 2, we can form a similar generating function, J1 of tau minus J1 of Z. But then what we're going to do here is I'm going to multiply top and bottom by, let's see, E4 of Z divided by E4 of tau. Okay, and this will give the generating function for this next one, and so on. In each case, you just pick the highest modular form, or the modular form with the highest order of vanishing, and do this structure, and that will get us that generation. So yeah, everything really does come down to the J function, these polynomials of the J function. Yeah, coefficients of the J function, and then one term here that's really controlling the weight. Yeah. So this works for all of the weakly holomorphic cases. In order to deal with the Poincare series or the harmonic Maass forms, again, we have a similar example of this duality, but we have to use the pairing to really see that. But it all kind of works out the same way. There are, in fact, generating functions in those cases. They're connected to what Zwegers calls the Green's functions for these forms. Yeah, and he does some work with that in his paper with Gross. Well, I think both of his famous papers with Gross and Gross-Zwegers papers, they end up talking about these Green's functions that generate these harmonic Maass forms for. Yeah, they're not thinking about them in terms of harmonic Maass forms quite the same way. They're thinking about real analytic modular forms and some other things. But if you go back to those and use the current language, it's all there. Yes. Yeah.
Modular grids, Folsom and an extension of this to the harmonic.
Oh yeah. Folsom, that grid, the same thing. Oh, let's see. That's a half integer weight though, isn't it? I can't remember the Folsom grid. I think that one's half integer weight. But again, you can get that using the Maass-Planck-Gray series. You can calculate the fact that duality has to exist the same way using the Bruinier-Funke pairing. It still works in half integer weight. Generating functions are going to look a little bit different in that case. But there are a lot of very interesting cases. Yeah. There's actually a lot of work on these modular grids. There were a lot of papers that were kind of different sort of ad hoc individual circumstances. A couple of years ago, I wrote a paper with Jenkins and one of his students where we tried to find all of these different versions of it and try to bring it together. So there's a paper that we wrote called Arithmetic of Modular Grids. If you're interested in it, that might be a good place to start. We try to look back at the history as much as possible to connect with all of these other versions of these modular grids that exist in the literature. Any what?
Combinatorial.
Combinatorial? Yeah, so one really interesting one is what's called the replicability formulas. So if you look at like monstrous moonshine, Norton, actually a previous paper by Norton, he talks about how to generate all of the coefficients of the J function, and in fact, all of the JM functions, just kind of going back and forth between the Heck operator, like looking at the JMs as images under the Heck operator, and then looking at the JMs as polynomials using the generating function. So using those two pieces, you can go back and forth and construct all of the coefficients of these, just starting with 6 coefficients to begin with. So that's one of the probably biggest initial combinatorial answers there. Yesterday in Ken's talk, he maybe talked about another one that can come up from similar results. You probably need a little bit more than just what I've got here to be able to get those, though. But yeah, certainly plenty of combinatorial results. Good. Any other questions here? Okay. If not, I'm going to pivot to another example of a harmonic Maass form. Let's see. Okay, I will do this one example really quickly, then I'll move on to a little bit more interesting one. But we talked about this in my talk yesterday, so I feel like we have to at least bring this up really quickly. So there is a very well-known Eisenstein series. This is just the invariant Eisenstein series, real analytic, but this is usually, I'm using tau. This is usually just defined as v to the s divided by c tau plus d, and then we sum over all pairs c and d that are co-prime to each other. Okay, or sometimes this is written as a sum over all pairs m and n that are just non-zero. You end up, it just changes by a factor of a zeta value. Okay, but this is a very standard Eisenstein series. Oh, I should write this. I'm missing a 2s there. Okay. So this is a standard weight zero real analytic modular form. It comes up in the study of Maass forms. It's under the Laplacian. This gets an eigenvalue s times 1 minus s. Okay, and so in the study of Maass form spectral decomposition, a lot of times you're looking at values of this with s real part equal to 1/2. Okay, so it comes up a lot in those applications. Of course, we're interested in harmonic Maass forms of more general weight, but we can get there from this. So what's oh, sorry, yes. Yes, thank you. Okay, and so it turns out that if I want a harmonic Maass form from this Eisenstein series, I can get there using this eigenvalue and a raising operator. Okay, so for example, let's take k bigger than or equal to 2, and I'm just going to look at e of tau, comma, I'm going to specialize, well, let me specialize after the fact, but I'm going to specialize s is equal to k halves, but before I specialize, I'm going to use my raising operator, k over 2 times. Okay? And if we do this, we will get something that is weight k, and it turns out that it will be harmonic. Okay, we get this right here is a negative triangular number. You do this raising operator, you're adding all of those terms, you get 0 at the end of this. Okay, now do we know a harmonic modular form of weight k? It might be related to an Eisenstein series. This is just going to be a multiple of the standard EK Eisenstein series. Let's see, I have the multiple here. Yeah. It's gamma of k divided by, gamma of k over 2. Yeah.
The whole theorem tells that this has to be a
Almost. This is like halfway in between Bool's theorem, right? Bool's theorem wants to go from negative to positive, and we're like starting right in the middle. But this is the eigenvalue that you would see using Bool's theorem if you stopped right at weight 0. So yeah, it's like halfway of Bool's theorem, but we apply this raising operator, and yeah, this changes, right? So if you look at your eigenvalue like this, the raising operator, as we apply this over and over again, this is going to turn into s minus k halves times 1 minus, let's see, what is it? 1 minus k halves minus s. And then s just kind of stays constant, and we're just changing this weight as things move. And so by the time you get up to k halves, s is already k halves, this becomes 0. It's harmonic. In this case, actually holomorphic. This is the usual Eisenstein series. Yep, the usual holomorphic Eisenstein series. Okay. Now we can go the other direction using the lowering operator. Okay. So I'm going to specialize. By the way, I specialized waiting to do the specialization until after I do the raising operator. That's important when k is 2. It doesn't really matter otherwise, but it avoids a pole that disappears in a derivative if I do this raising operator first for k equals 2. Okay, I'll talk about that in just a moment. But otherwise, let's look at this. Let's look at L of tau comma 1 minus k halves. So that's the other eigenvalue here. Okay. Oh, actually, you know what? It doesn't really matter. I think my notes, I think I kept this at k halves. Where am I at? Even weight, lowering. Oh, yeah. Okay. I decided I wanted to keep S positive. It just works better with our convergence. We have to use analytic continuation for our smaller s anyway. So I'm going to keep this. Positive. But then I'm going to do a lowering of 1 minus k halves. Okay. Now this is going to get us something that is harmonic. But it will not be holomorphic. Okay. And this is the piece in my diagram yesterday that's kind of right in the middle. It doesn't really fit into, well, it's not an h of 2 minus k. This object here, well, it's going to have, it's going to look, there's going to be some multiple out front. There's going to be a v to the 1 minus k plus, what else did I have there? I'm trying to avoid writing out the full terms here. But yeah, so a v to the 1 minus k and then some other constant here. Okay, so we've got, we don't have a exponential growth. Oh, I've got k as positive. But we're going to have polynomial growth here. Okay, so it doesn't fit into not in h of 2 minus k, but just barely. Okay, it does fit in. Is in h2 minus k thing. Okay. Well, this is the thing. in my diagram, if you act on this with a C operator, you end up getting a multiple of your standard holomorphic Eisenstein series. If you act on this by the dk-1 Boole operator, you get a different multiple of your holomorphic Eisenstein series. Okay. Good. Any other questions there? Okay. Again, this one isn't often studied in isolation, just because with the real analytic Eisenstein series, it's often just kind of studied all together as a single function, but it does exist and does fill in an important part in our space. Okay, let's see. What is my end time? 10:45. Okay, so, okay. No, it's fine. I'm just gauging this next step because I can take more or less, but that's good. Okay, where's my eraser? The next example that I want to look at are things called Weierstrass Maass forms or Weierstrass Mach modular forms. So this is my next example. Of our Mach modular forms or harmonic Maass forms. And these come from the theory of elliptic curves. Okay, so I'm going to really quickly review elliptic curves. I'm going to assume a certain amount of familiarity. If you don't have familiarity, please feel free to raise your hand and ask questions. But I'm assuming that I have an elliptic curve with a rational equation, okay? And we know that if I take my elliptic curve and I look at, well, it has a group law. Okay. If I look at the points over the complex numbers, okay, along with this group law, I know that this is isomorphic to the complex plane, the additive group of our complex numbers, modulo some lattice connected to our elliptic curve. Okay. More or less familiar to everybody? Okay. So now Weierstrass theory gives us a way of sort of parameterizing our elliptic curve. Okay. So one of the things that we're going to start off with is the Weierstrass P function. And at the point of the P function, we're going to create a function that is lattice invariant. Okay? So this is a function that's going to take in a complex number, but it's only going to depend on the class modulo the lattice. Okay? So shifting by a lattice point does not change the value of the function. Okay? So in order to do this, we're going to, so P of z is going to be 1 over z squared plus the sum over, so lambda in my lattice, but not the 0 point. Okay? This out here is the term corresponding to the 0 point. And what I want to do is I want to look at 1 over z minus lambda squared. Okay? This is what I really want, but this doesn't converge. So in order to make this converge, I'm going to add 1 over lambda plus z over lambda squared. Okay? And this will converge. Now the coefficients of this are the Eisenstein series, or Eisenstein numbers. So we have P of z is equal to 1 over z squared plus the sum of, so k equals 1 to infinity of 2k plus 1 times g of 2k plus 2, which I'm going to write as a function of the lattice, z to the 2k. Okay. What's that? Oh, I'm sorry. I am minus 1 over lambda squared. I'm looking between two parts of my notes. I apologize, I'm being dyslexic on my notes. I will write that correction term that I just wrote there in just a moment. This is the one that we want. Yeah, a very much simpler correction term here. Yes, thank you for that. So this is the correction term we want. And we look at our Taylor expansion, and you end up getting these Eisenstein series here. Okay, these are you can write these as weighted values of the standard Eisenstein series. Okay, where tau is going to be the ratio of your periods of your lattice. Okay, but these are the Eisenstein numbers that show up. Now notice we don't have the weight 2 Eisenstein series. That's not modular. Okay, in a certain sense, you can kind of think about this piece right here as kind of getting rid of the contribution that really wants to belong to that weight 2 Eisenstein series. Now, the next thing that I want here is it's called the Weierstrass zeta function. Okay, the Weierstrass zeta function is an antiderivative of the p function. So this is going to be 1 over z plus the sum of lambda in our lattice, lambda not equal to 0. And here, this is where we're going to have what I said before. So we're going to start with 1 minus 1 over z minus lambda, but then I need to add 1 over lambda plus z over lambda squared. Okay, so this is what I need in order to make my sum converge. Now we have this property that the Weierstrass p function is equal to the negative derivative of our zeta function. Okay. Now there's a problem though. The Weierstrass p function is lattice invariant. The zeta function is not. And so in order to create something that's lattice invariant, Eisenstein sort of corrected this, decorated it with a couple of terms. So I'm going to put a hat on this for the corrected version. This is going to be our standard zeta function. And then we're going to subtract off the term I'm going to call this S of lambda. This really is the non-holomorphic weight 2 Eisenstein series component. I'll write this in just a moment. Times z minus pi divided by the volume of the lattice. So this is the area of a fundamental parallelogram inside of our lattice, times z bar. Okay. So this corrected term, this corrected version, is lattice invariant. Okay, and again, what do I mean by that? Z hat of z plus lambda is equal to z hat of z for all lambda in my lattice. Yeah, so S of lambda here, S of lambda is equal to the sum over lambda in my lattice, lambda not equal to 0, of 1 over lambda squared times the absolute value of lambda raised to, I shouldn't use S here, let's say a t, and then we're going to take the limit as t goes to 0. Now, if you've ever seen Hecke's trick to get the convergence of the non-holomorphic weight 2 Eisenstein series, that's exactly what's going on here. Okay? This is the weight 2 Eisenstein number for our lattice, for our elliptic curve. Okay? So we need that contribution here times z there, and then we need this part, this non-holomorphic correction. Now, in the perspective of the elliptic curve, this corrected zeta function kind of fills in the same space as harmonic Maass forms in terms of our modular perspective. Okay? Specifically here, we're trying to look at a antiderivative of a meromorphic function. Okay? The standard way to do that doesn't work. We have to find a harmonic version to get something that actually is a function on our the variety we're looking at, okay? Our C modulo of the lattice. Okay. And so this is our harmonic function that is a antiderivative of our meromorphic function P of Z. Okay. Now, where do we go from here? Well, there's this thing called the modular parameterization of the elliptic curve. This is a way of getting points on the elliptic curve using, coming from a modular curve. And that relies on a cusp form. So related to our elliptic curve there is some cusp form Fe in, this is going to be S2 of, say, gamma naught of n, where n is the conductor of the elliptic curve. Okay, I won't go into what that is, but this is related to the modularity theorem that tells us that these always exist. Okay, we always have this cusp form connected to our elliptic curve. Okay? The next thing that we're going to use is the Eichler integral of this. So I'm going to say this curly E can equal minus 2 pi I, the integral of tau up to I infinity of Fe of tau, I'll just use a W, dW, okay? So this is just an antiderivative of our cusp form, okay? And it's all normalized so that if you use the D operator on the Eichler integral, you will get the cusp form. Okay? So the derivative gets a cusp form. This is something that is truly holomorphic or truly modular. Our Eichler integral is not truly modular, but if you look at the obstruction to modularity, so let's go ahead and take a matrix. So let's let gamma be in gamma naught of n. Okay, so one of our matrices in this congruent subgroup, and we're going to look at our Eichler integral at z minus the Eichler integral of gamma of z. Okay. Now again, if I take the derivative of this, I get a modular equation for my cusp form. So the derivative has to be 0. That means this cannot depend on z. This is independent of z. It only depends on lambda. Okay. And Eichler-Shimura theory tells us that this map, let's say C of lambda equal this, okay? The image, this is going to take gamma naught of n, and it's going to take us into our lattice. This is mostly true. There's a couple of hypotheses in here, fudging a couple of terms, but let's just go ahead and leave it here for now. Okay? This difference should give us something in our lattice, okay? At least up to some factors. Okay? Does this make sense? Okay. So the way that we use this to create modular parameterization, okay?
Modularity theorem.
Oh, sure.
It looks like you need it, but they started with modular form of it to construct the lattice, you see.
I see. So they started with the modular form, and they're looking at the elliptic curves.
Start with the modular weight and then construct your elliptic curves.
Right. So this works perfectly good for every elliptic curve connected to our modular forms.
The way you said it, it looks
That's true.
So you need to kilowatt.
Sure. Yeah, that's true. Yeah. So that's definitely a better approach since I'm starting with my cusp forms anyway. Yeah. So start with our cusp form. We can create this. Now, the original use of the Weierstrass P function. Okay, we can use the Weierstrass P function say P of Z and its derivative, okay? And this actually is a point on at least some model of our elliptic curve. And I'll say E over C. If I allow Z to be any complex number, I can get a coordinate for some model on my elliptic curve. Okay. Now, what we're going to do here for the modular parameterization, so the modular parameterization is going to be a map from our, so H mod gamma naught of n. So this is our modular curve. Okay. And we want to go to our elliptic curve over C. And what we're going to do here is we are going to take our Weierstrass P function, okay, or the derivative, okay, or yeah, both of them. But I'm just going to look at this initially just with the Weierstrass P function, and I'm going to plug in my Eichler integral of tau. Okay. And once again, if I act on this with a matrix, I'm going to get back to the original point plus a lattice point. So this right here is a modular form. Okay, this is, at least it's meromorphic. It's a meromorphic modular form of weight 0. Okay. Meromorphic modular form of weight 0. Okay. Now, to my knowledge, Pavel Gershoy was the first person to do this next step. It wouldn't surprise me if there was somebody else, but I just don't know. I haven't seen anything else in the literature. But what Pavel did was he took Eisenstein's corrected zeta function and he plugged in this Eichler integral. Okay. Now, once again, this Eichler integral, you act on this by a matrix. The Eichler integral comes back to itself plus a lattice point. The corrected zeta function is invariant under the shift by a lattice point, and so this is modular. Modular of weight 0. Moreover, it's harmonic. Okay. At least at every point that we don't have a singularity. Let's say apart from meromorphic singularities. Okay. And so under certain conditions, this gives us a harmonic Maass form. Okay. So let me write it this way. So if the degree of the modular parameterization is equal to 1, this is the easy case. This tells us that there's only one pole coming from the parameterization, so coming from zeta itself, which ends up having to be at infinity the way that we've constructed this. Z hat of our Eichler integral will actually be in H of H0. Yeah, of gamma naught of n. Okay. And so in these circumstances where this works, this gives us one of the most explicit calculations for these coefficients of the harmonic Maass forms that we have. Okay. So there's an example. Let me write down, I won't go through all of this, but one very nice example of this involves the elliptic curve. I'm going to use the Cremona label. This is 11A1. So this is the strong Weil curve of conductor 11. Okay, it has. Well, I can give it the equation y squared plus y is equal to x cubed minus x squared minus 10x minus 20. Okay, The cusp form that comes out of this, the F11 here, is equal to Q minus 2Q squared minus Q cubed plus 2Q to the fourth, etc. So that means the Eichler integral, we're just going to integrate each of these coefficients. This will be Q minus Q squared minus 1/3 Q cubed plus 1/2 Q to the fourth, etc. This is an elliptic curve with rational equation, and so that means the coefficients of the P function are all rational numbers. So P of Z is going to equal 1 over Z squared plus 31 over 15 Z squared plus 2501 divided by 756 Z to the fourth, etc. Okay, I can integrate to get the Weierstrass zeta function. If I take the Weierstrass zeta function and I plug in this Eichler integral, okay, I will get a Q to the minus 1 plus 1 plus 4/3 Q plus 7/6 Q squared plus 2/9 Q cubed, etc. Okay. Now this is the ordinary Weierstrass zeta function. In order to get our harmonic Maass form, we need to add two things to it. Okay, so I need this S of lambda value here. Okay, I'm going to add this plus a multiple of the Eichler integral. Okay, this right here is 0.381246 ... Okay, this is a 1. Yeah, 4/3, 7/6, 2/9, and so on. Okay, so these are all rational, but then we have to add this multiple of our Eichler integral. Okay, so our coefficients of the harmonic Maass form are going to be transcendental. The only source of the transcendence is this value, this S value right here. This is the transcendence for these coefficients. Okay. And so if I actually plug this in, my Z hat of the Eichler integral, I'd end up getting a harmonic Maass form that starts Q to the minus 1 plus 1 plus 0.95, etc., Q plus 1.54, and so on, Q squared, and so on. Okay, and so if you calculated the harmonic Maass form just using maybe like the Poincare series, this is what you'd see. You'd see these kind of nasty looking coefficients that are transcendental, okay? But hiding behind that, okay, that transcendence, there's only a single value here that controls all of the transcendence, and then behind that we have these rational coefficients, okay? So that's one of the beautiful things that you can see very plainly from this perspective of these harmonic Maass forms. Okay. We can construct something like this for every rational elliptic curve. The end result might have these meromorphic singularities on the upper half plane, but there is a way to remove those, not very explicitly, okay, but we can move all of those singularities to the cusps, okay, if that's something that we're set on doing. Okay. So that's, I think, where I'll end there with this last example for our harmonic Maass forms.